Good morning, everybody. This is your, I keep on forgetting what I am. The virtual CNC machine shop instructor, Ed, the CNC dude here, with my Tampa Bay Rays hat on. I miss the Tampa Bay Rays. I'm also wearing a shirt from my friends in New Hampshire, the Muchachos Drum and Bugle Corps. Oh, over here. I used to be a member of them, and I used to actually teach the drum line at one time when I played the snare drum. Okay, we're going to talk about feeds and speeds. And in your Google Classroom, I put in this, it's not really an assignment, but reading. And Fusion 360 Adaptive, which technically is called trochoidal milling, roughing strategies, and all this adaptive stuff. And it applies to other products like Mastercam is one called dynamic milling. It's they're all roughing. They're not meant for finishing. Material removal, and I think Titan's going to have a webinar on material removal rate (MMR). So, and how you can gain time and efficiency no matter what kind of machine you have. So. All right, I find that the first thing a lot of people have no idea about is what feed and speed do I run. You know, if I'm in this project here and I'm running this end mill right here, right there. Edit, right? Feeds and speeds. I actually made my own tool library. So I have my Titan building block and my STC Titan building block. And this would be the active one. So let me shut this one off and local tools off. Okay, we got two being shown right now. Two setups actually. Two setups are active. But I'm pulling all my tools out of this area. So what I did is to do that, I'm doing it to save time first of all, and yeah, save time. So if I'm in the 1/2-inch flat end mill, the one we use the most, the 3-fluter, in feeds and speeds, I've already upped my game here because I said the TM1 can run 6,000 RPM. Now, where do I get all these numbers, right? Let's go into this. This is a real basic feed and speed chart for carbide end mills, right? Right up here it says aluminum alloys, which is what we're cutting. And you get all these different materials. You're not going to have all the materials on there, but this is a pretty good indication. All right, SFM, surface feet per minute. I'll have to link the Haas Tips video on this, which is an excellent video on the what I call the big trailer tire and the little trailer tire. You're going down 75, and you're towing your boat trailer, and next to you is the big tractor trailer. You're both doing 60 miles an hour. Well, we know they're probably doing 80, but which tire is rotating faster, which is RPM, right? Your little boat tire. So the little tools got to spin faster than the big tools to keep up. So that's basically, and in reverse, you can't be spinning the big tools too fast. They'll burn up, rubber will be flying off. All right, so this is a recommended surface feet. It says right there, recommendations for their tools, which is pretty much all carbide end mills. 600 to 1200 surface feet per minute. And then you got these other 3 rows right here. This is what we call chip load or feed per tooth. So right there, feed per tooth. So if you have a 3-flute end mill and you up to 1/4 inch, just saying you can go from 2/10,000ths of an inch, 2/10ths, to 2/1000ths. And then when you get into the 1/2-inch range, 2/1000ths to 4/1000ths. Then when you get to the big honking ones there, 4 to 8/1000ths. Well, morally because they're more rigid, It's not about horsepower of the machine so much. It's like how rugged is the tool. All right, so we take these parameters, right, here, and I'm saying I'm just machining on the fly. I load these things in. Titan tells me to put in 4,000 RPM. I'll do 4,000 RPM. But like, well, wait a minute. I know a little bit more. I can go 600 surface feet per minute, right? That gives me 9,167. I'm like, oh, I'm at a new shop now. They have 10,000 RPM machines. That would be fine. What is 1,200, right? See, this self-calculates. 18,000, well, I guess I can't use that, right? So, in other words, in this case, I'm in a 10,000 RPM machine. I'm going to run 10,000. And notice this one says ramp spindle speed, so I'm going to change that one too. All right, down here is feed per tooth. I forget what it said before, but it says 1,000ths and 2/10, and that chart said 2 to 4. So if I even just go on the conservative side, let's just go conservative, right? I actually am kind of conservative. 650 is not very, that's on the low end of the RPM scale. That gets me 60 inches a minute, right? And this should be just fine. It's not like going crazy. And you have some basic parameters. These are all basic parameters. And they're all how long is the tool, how much is it sticking out, how rigid is your setup. So if you talk about standard in the vise parts in there, pretty good. You don't have a tool that's like this long. These will work all day long. There's some other notes down here. I didn't discover these notes until I actually started reading them. TIN, increase speeds by 10 to 25%. You wouldn't use TIN on aluminum. A lot of them, those end mills are uncoated. But you can use TIALN or TICN. I've run TICN. Notice up in here, you can increase the speeds like 25 to 50%. So you can actually do some more stuff here. And it says for lighter radial. Radial's like a radial tire, like sideways, radial. Lighter radial depth of cuts, which in tricoidal, that's what it's doing. It's doing very light sideways cuts. Higher range of surface speeds should be used. So for greater radial depth of cuts, which means you're taking bigger chunks sideways. Lower range. Slotting should be reduced. Slotting is considered to be the toughest thing for an end mill to do, because you're plowing right through like a boat through the water. So you're plowing right through, the whole front of the end mill's just chugging away. And if you're running a high-speed end mill, they'll actually deflect and bend a little bit in the non-cutting direction. So it's almost impossible to cut a slot dead on with just an end mill going forward. It'll probably be a little tapered, and the finish might not look the best. So slotting is kind of going away because of this tricoidal tool path, which can only be...
You have 15 minutes left of computer time.
Getting kicked off the computer again. Okay. By this new modern adaptive tricoidal dynamic milling strategies. All right. And here's it. When used exiting long, end mills reduce feed per tooth by 50%. Remember, these are recommendations. So if I was cutting something new, like we was cutting titanium, I plugged in some numbers. There was some right here. At the machine, I say, I think my RPM is okay. I am unsure about my feed rate. So I take and I reduce the feed rate by 50% at the machine, because I'm not sure. It's all new. I might be doing tool steel, a new stainless. And I'm going to listen to it, watch it, watch the load meter on the machine. Oh, it seems to be cutting just fine. 80%, 100%. Yeah, it looks good. You're learning as you're going along. We're always just learning. So this should be your go-to basic chart when you plug these things in. And what I meant by the saving time is, if you have all these tools already laid out with the RPMs already, then it saves you a lot of time filling in this space over here, especially in this one. So now your feed rate also can affect surface finish if you're going really blazing along. So the surface finish stuff you may want to do a little bit more conservative than the roughing stuff, you know. And a lot of that just comes from experience. If you stay in these those ranges there. Now in here is a discussion on tool path strategies with the adaptive. I have a playlist here of various dynamic milling. Dynamic milling is becoming a very hot area, tricordial style milling. So I have a couple discussions on there, one on cam settings for your Haas machine, NYCNC 2D adaptive, one on end mills, Niagara end mills. Warding chatter is a good one from Haas. How to change the max feed rate on your Haas, because a lot of them don't come out of the factory with the blazing speed that they're capable of, so you can change them. I think the next gen control, you need to buy the parameter thing. So this was testing Helical. Helical is a company, not I actually pronounced it wrong. So MQL, which is a new air blast with a little bit of lube system. A Shunk hydraulic holder. These are becoming very common in the steel cutting tricordial style. Another one here on dynamic milling, tips and tricks with the vise, 7 flute end mills. Actually, we're now getting into, and I think Titan was showing a video with a 5 flute core end mill, which in my thinking, people that I know, we're all using 3 flutes in aluminum, but maybe this is this new CAD CAM stuff is making us think a little bit more. Some Sandvik stuff. Sandvik's got a lot of good stuff on cutter technology. They're a carbide insert company. Talking in the roll-in technique in machining. So a lot of videos here. I actually left these ones in here. These are actually, I believe SurfCam was the first one that came up with this style. Okay, let's go back to this. These are the end mills we were using to cut the titanium with, and this is the HS series. I started realizing that especially this really applies more to steel cutting than aluminum. Aluminum you can get away with anything. The helix on the end mill, it was a variable helix, and I started seeing that word over and over again. I'm like, oh. Every end mill company seemed to have a variable helix end mill. That's for this tricordial style milling. This is 4 flute, 5 flutes. These right there, variable index, 7 flute. So, and in this one,
You have 10 minutes left of computer time.
Okay, I'll be done in a minute. Had some feeds and speeds in here, so. Let me go back. And the last one was settings that I'm using in class. Discussion on heights, settings in adaptive. I took some screenshots. Heights model top. Passes. This is from Titan 1M, stock to leave, and some of the settings, because honestly I was forgetting them too. Passes adjust. Optimal load is the radial engagement, this number right up here. I haven't quite figured out the minimum cutting radius, but they give you a little picture if you put it over there. Machine cavities being checked on, and this one here is maximum roughing step down. Now, the tricordial style, the advantage is, instead of, we used to use pocket and go down in steps, like cut up and go down, go down, go down. Now, because you couldn't go full depth, it would buzz like crazy. So now you can go full depth because you can go sideways in small steps. So to get it to go full depth, you got to play with this number here. This number just needs to be bigger than the deepest part. So, and then your stock to leave numbers. You got to leave stock with adaptive. And linking parameters. I was reading some other people that were using 50% stay down. There's a lot of discussion on that, meaning stay down versus coming up and rapiding around. Okay. Lift tight. Tighten uses 0 and 100. Lift tight is what they call a micro lift. You cut in one direction and then you got to retract because you're always climbing, like cut, reposition, cut, reposition. So it goes and cuts, and then it got to go back and reposition. If you leave it on 0, it's actually just it's like dragging on the floor again. So you're like, if I pick it up just a smidge, 10 thousandths, and go back to where it was, and then I increase the feed rate of 400 inches a minute because that's as fast as the TM1 will go, which actually picks up some time. It's the non-cutting areas. When I used to first see this style, it used to freak me out because I was trying to watch this and going, hoping this doesn't crash, but got comfortable with it. And this is helical entry, and then you got settings like ramp diameter and minimum ramp diameter. So sometimes I've had to squeeze the helix small because it wouldn't do it. You picked it, but it still showed a straight line. And sometimes you got to play with the size of the spiral to get it to go in. Some more settings. How to reduce your post size. We just ran into this with a graduate. They have their own machine now. First of all, I'm using cloud post, so we only have posts that we're using. And I had modified our posts so we had the coolant in the right area, and I put our name on the top, and I modified the tool list a little bit. And I had it to shut off sequence numbers, so they automatically come shut off. That'll save space. The thing about this adaptive cutting is it creates a lot of code. And especially if you don't have the expanded memory, you're probably going to be running off the USB in the FNC mode. And I prefer to run the program in the memory. All right, so we try to shrink up the program. That's an easy one. Remove the sequence numbers. They're not needed. Okay. Another thing to do is smoothing. See adaptive up here? By changing this tolerance, it says right here, it's smoothing, aka the arc filter. It's going to create, to make a curve, it's going to create a crap load of G1s, to go from like here to here might be 100 lines, when it might be like 2 arcs, impossible arcs. So you're saying if the arc can be made within 2 thousandths, make it a G2 or a G3. By doing that, you're shrinking the code up. So we experimented that.
You have 5 minutes left of computer time.
Already. All right. We cut a program size 25 to 50% just by doing that. And I had a list of videos here, but they're on the playlist. So that's pretty much my talk on this area. So if you already have a tool list library, then when you're putting them in, less work in this area. But believe me, on the fly, you're going to be changing these numbers because you're going to be thinking about your strategy and going, oh, I don't know if that little teeny end mill can really do that. Let me plug all these numbers in. Now, when you're in Fusion, when you change this number, it only changes cutting feed rate. It does not change lead in and lead out. It's a very small area, probably not worth your time. But if you want to play with that. But if you're wondering why this affects that number, and it's also relative to the RPM. So you want to have the RPM first. So if you base everything on SFM, you'll know where you're at. But you really need to know your machine's capability. Then you have plunging feed rate. Now, if you're actually literally plunging in, which is ramp milling would be plunging or plunging, um, I had a rule of thumb that I would use the cutting feed rate divided by 2. Just as a starting point. And that's pretty much all you need to know on the feeds and speed stuff. And you want to get knowledgeable about this so you can start plugging these in, see if they work. And if you get on the job and you're actually doing this kind of stuff, even at the machine, I'll do some temporary feed and speed tweaking, turning the knob of the button and going. I looked at the chart and they're running this thing like 2,000 RPM. I think it could go 7,000 RPM. I'm not gonna twist the knob right up, so I'm just gonna let me go another 20%. That sounds fine. So I can make improvements on the floor and edit the program at the floor, which is why you need to know G code. And I would, when I was on the floor, I'd write the notes and we return the program to the programming room, and they would review it and say, yeah or nah, so, and then you can butt heads later. So anyway, that's the way it is in a shop, but my fun old days. And eventually I end up in the programming room, so I had to listen to everybody. I could tell you good stories, but enough of that for now. So I just want you to watch this video, a very important video on just getting the start of feed and speed implementation and knowledge. So thanks, and I'll talk to you later.